Calculating the nth Fibonacci number is the hello world of teaching dynamic programming, and I'm not going to break with tradition. Using a simple example will help us develop a method for solving more complicated problems later on. In our implementation of the Fibonacci series, the first number is 1, and the second number is 1, and each number in the series is the sum of the previous two. The numbers in the series grow very fast, exponentially in fact. When we want to calculate the nth Fibonacci, say the 6th Fibonacci number, we first solve two types of subproblems. The first is to calculate the previous Fibonacci number, and the second is to calculate the previous Fibonacci number. Once we solve those subproblems, we just need to add them up, and we're done. What's the base case? In our implementation, the base case is when n is 1 or 2. In both cases, we return 1. Let's code this up in our Jupyter notebook. First, some unit tests. Now the base case. Code the subproblems and test it out a bit. Now I want to get a rough idea of how long these calls are taking. So I'm adding the magic timeIt command before each call. timeIt runs the function through a lot of loops to get a more accurate number. So I'm going to speed up the playback here, just so you get an idea of the difference in order of magnitude. For example, Fibonacci 6 takes about 2 microseconds, but Fibonacci 20, which is just 14 numbers away, is 1,000 times slower. Let's draw the recursion call stack for getting the 6th Fibonacci number. Fib6 calls Fib5, which calls Fib4 all the way down to Fib1 and Fib2. Then backtracking. Fib4 calls Fib2, going up another call to Fib3, and then the other half of the tree down the call stack again. How many times is Fib6 called? How many times is Fib5 called? How many times is Fib4 called? You'll have some exercises to work out the formulas here. It's especially interesting to calculate how many leaves this tree has, because each leaf corresponds to the base case and contributes 1 to the time complexity. In any case, you can see that the tree gets very wide very quickly, and the naive recursive algorithm has to be improved. Since we're constantly calculating and recalculating the same subproblems, we can use a technique called memoization to speed up the algorithm. Memoization is just storing the output of the function so that we can reuse it instead of executing the same recursive call over and over again. So returning to our example of calculating the 6th Fibonacci number, when we call Fib5, we ask, have we calculated Fib5 yet? Do we have it stored? If yes, we just use the value. If not, we carry on as before, calling Fib4 and Fib3 with the intention of adding those values up. We continue down the call stack because we still haven't stored anything since we haven't ever actually returned anything. When we reach Fib1, we store its value in a memo. That's the origin, supposedly, of the term memoization, and return the value 1. Then going up, we have a call to Fib2, and we store that too before returning the value 1. Now Fib3 is calculated from the sum. We store the value 2 for Fib3 and return 2. Then going up, we have another call to Fib2. We don't need to calculate that. It's stored in our memo. We can calculate the value for Fib4, store 3 in the memo. No need to calculate Fib3. We have it. Add 2 up with 3, store 5 in the slot for Fib5. Do we need to calculate Fib4? No, it's already in the memo. Just add 5 and 3 and we have our answer, 8. Let's code this up in a notebook. I like to use a decorator to memoize if possible. It's nice because you don't touch your original algorithm. Your function is already debugged, and besides, the recursive algorithm is very clean to read. You clearly see the subproblems. It's really beautiful. Let's not mess it up. So I'm going to decorate Fib with a new function called memoize. Memoize takes a function as an argument. Inside memoize, we have a dictionary for storage and a helper function. The helper function will work with the decorated function's input, in this case n, so I'll call the input variable n. The helper checks if n is already in the dictionary. If it is not, we call f on n and then store the result in the memo. Then, in any case, we return the contents of memo at place n. The memoize function returns the helper function. I'll leave it as an exercise for you to test this and profile it too with the time or time it magic commands to see how powerfully effective memoization is. Let's go back to the call tree one more time, because there's another thing we can do to make the algorithm even cleaner. If you notice, with memoization, although we're working top-down, we're not actually recursing very much. We're filling the storage from the first location onwards. So in effect, the algorithm is almost bottom-up. You can see the order of the subproblems, from smallest to largest. We can rewrite the algorithm iteratively, and then we won't have these calls to fib2, fib3, and fib4, and we'll calculate the sixth Fibonacci number by calculating the first number, then the second, then the third, and so on. Going back to our notebook, we'll write another decorator function for fib of n. I'm going to copy the memoize decorator and just make a tiny change to it. This decorator is called iterate. The only change is that here, where we previously would call fib on n, I'm going to iterate on all the values up to n and fill up the array. Again, I'll leave the testing and profiling as an exercise and see further down in the notebook some more fun quizzes and problems. In this lesson, you saw the incredible effect memoization can have on the running time of an algorithm. We went from exponential time to linear time with just a few lines of code. In the next lesson, we'll apply what we learned here to another cool problem.